Okay, so let's now see a candidate protocol for achieving oblivious transfer. Of course, I told you in the previous video that oblivious transfer was impossible, but who said you shouldn't try the impossible? Let's give it our best shot. So here's how the protocol works. In the first stage, Alice is going to prepare a bunch of BB84 states, 2n of them. So Alice is going to choose randomly some angles, theta I, random bases, and some bits, xi, for I going from 1 to 2n, and she's going to send to Bob the corresponding BB84 states, so xi encoded in basis theta I. Now Bob receives the states, and he measures them in random bases. So Bob will choose some theta tilde I, and he measures and obtains some outcomes x tilde I. Once he's done, he tells Alice, done, alright? Then Alice sends over to Bob her basis choices, so theta 1 up to theta 2n. And Bob is going to do the following. He's going to define two sets, I and I prime. I will be the set of indices I in which he made the correct guess. Theta I is equal to theta tilde I. And the complement I bar will be the set of I such that they're different. For simplicity, let me assume that each of these sets has the same size n. Because Bob's measurement bases were chosen at random, they'll be approximately of size n. For simplicity, let's assume they're exactly of size n. And now he's going to set an interval I, y, depending on his input y, which is a bit, equal to I, and I 1 minus y, the other one, equal to I bar, and send I0 and I1 over to Alice. So, depending on his input y, Bob puts the set of bases that he correctly guessed either in I0 if y is equal to 0 or I1 if y is equal to 1. Alice doesn't know this, she gets the two sets, and what she does is that she replies with her bits XORed with her secret string depending on the interval I. So she'll send two things. One is x I0, so these are the bits x indexed by the values in I0, XORed with S0. So if my set really has n indices, S0 is a n-bit string, so I can do this, and then xi1, right? Let's have these be n-bit strings. She sends this over to Bob, then Bob simply outputs sy, which will be equal to what he received from Alice for the y, let's call it t0, and this t1, so he computes ty parity with his own outputs, x tilde I y. That's the protocol. You can check that it's correct. Why is it correct? Because I, y is a set of indices for which Alice and Bob made the same choice of basis. So they got the same outcomes. So when I look at t, y, and I XOR Bob's outcomes x tilde, these are the same as Alice's outcomes, so they cancel out, and Bob indeed receives Alice's string sy. So the protocol is correct. Is it secure? Well, what's the intuition here? What can they do? So cheating Alice really cannot do much, because what does she receive from Bob? A done message here, alright, that's not too helpful. And then two sets of indices, but if Bob really chose his bases at random, then these indices are random. They're just whenever Bob agreed with Alice, but whatever Alice does, this is going to be 50-50, uniformly at random. So security against cheating Alice does work, this is safe. Now what about cheating Bob? We don't want Bob to learn more than one of Alice's strings. How would he be able to learn both strings? Well, he'd have to be able to decode from both T0 and T1, which means that he'd have to know both Alice's inputs in I0 and in I1. In order to do this, he has to have measured using the correct bases both in I0 and in I1. Now, if he chooses his bases at random, that's not going to be the case. You could be worried by the way that Alice puts some of his correct guesses in I and some of them in I bar. He kind of hedges his bets, and this way he'd be able to learn parts of S0 and parts of S1. This is true, but there's a workaround around this which uses privacy amplification that you learned about a couple weeks ago in order to get rid of that problem. So you can show that if Bob does make a random choice of bases, even if he tries to hedge his bets, there's a simple modification to this protocol such that he won't get to learn any information about Alice's two strings. Really, the best he could do is put all his correct guesses in the same set. Alright, but all this hinges on Bob making a random choice of basis, and he doesn't need to do that. In particular, maybe you've already noticed there's a simple attack against this protocol, which is simply to wait. Bob will not measure, he'll say done. Without having measured, then he'll wait for Alice's basis, theta, and then only measure using the basis information he got from Alice. So Alice is giving away too much information here. She's trusting that he's measured when he says he's measured. That need not be the case. So the protocol is not secure against cheating Bob. Now there's two ways around this. One is to enforce a little bit stronger assumptions, put a technological requirement on Bob. This is called the bounded storage model, and we'll learn about that next week. Another way to get around this would be to use the idea of a commitment. What Alice will do, instead of asking Bob to just say done and trusting him on faith, is to ask him to commit. So we'll replace this by a commitment. Bob will have to send to Alice some kind of a tag that commits him to having made measurement in certain bases and obtained certain outcomes x tilde. This commitment should be such that by itself it doesn't reveal any information about the choices that Bob made, because otherwise this would let Alice cheat later on, but it should be such that Alice can still check it. Meaning if Bob commits to something, once he's committed to it, there's no way to change his mind later on. So that's called a commitment. You can show that if you have a secure commitment protocol, then this OT protocol can be made secure. And so the only thing that would be left in order to achieve oblivious transfer is to implement bit commitment, and that's something that we're going to think about in the next video.